welcome.
All right, thank you very much. So hello everybody. Thank you, Katia, for the invitation. I'm very happy to have the opportunity to talk here about some of the works that we have been in collaboration. We have been working on collaboration with Andoni Garcia, with Ruyu Lei, Yushuan Lin, Tinsu, and Cristobal Meroño. The title is only about the Calderon problem, but I'm going to talk about 3 different works that I have been developing with these 3 group of people. So I will focus mostly on the work with Andoni Garcia because essentially I would say it's the more, it's the easier to follow. It's where some of the ideas are started to be. And then I will talk about some of the extensions for Maxwell equations and another extension to understand what was going on with the model for the noise that we had it here. So let me introduce the contents of the talk. So first I will introduce the Calderon problem that probably most of you know perfectly. I will talk about how you reconstruct the conductivity on the boundary, this problem without noise, so ideal data. And then I will talk about the problem with noise, the Calderon problem with noise. Then I will discuss the results with Andoni Garcia about the reconstruction on the boundary using noisy data. Then we will talk about the modeling the error. I have to confess that when we started working on that, we didn't know anything about the stochastic approach. So one of the things that we had to learn is how to model the error. And that's why I wanted to spend like a few slides talking about how to model the error, or at least the way we did it here. Then I will talk about the extensions, which include the extension to Maxwell equations, and another extension about where are the limitations of the way we have modeled the error. Not the limitations of the modeling itself, but just the fact that the noise can make the signal lost. So that's what we discussed in one of the extensions, and eventually I will try to sum up some of the key points that I could keep in mind. So let me start by talking about the Calderon problem. So the inverse Calderon problems aims at determining the conductivity in a non-homogeneous medium from making some non-invasive measurements. So that's roughly the general idea, and in mathematical terms, it essentially consists in given an electric potential described on the boundary of a domain D, this electric potential induces another electric potential in the interior. This electric potential in the interior satisfies this elliptic PDE, or this Cauchy problem on the boundary, and the gamma times the normal derivative of U on the boundary, this term that I pointing here, it models the outgoing current density through the boundary. So then non-invasive measurement could be think of having electric potential on the boundary and the current flux on the boundary. So for this non-invasive measurement is assumed to be taken as the Dirichlet-Neumann map, which takes this Dirichlet data F into the Neumann data gamma times the normal derivative U at the boundary. So that's, for us, will be the boundary measurements, and we will call it like many times DM map, just DM map. So then the inverse Calderon problem, as Calderon formulated, was to decide if gamma was uniquely determined by the DM map, and to calculate the gamma whenever there is unique determination. So just a few comments on the model that maybe are trivial, but that's the one that are motivating our work, is that this problem originated as in electrical prospecting, and aims at determining the conductivity by means of a steady state electrical measurement. That's regular motivation. But then what happened is that the non-invasive measurements are assumed to be this lambda of gamma. That are assumed, this data is assumed to have through making some measurements effective on the boundary of the domain. The model assumes two important points. Assume to have infinite many pieces of data, and also assume to have infinite precision measurements. So that's like essentially to know the graph of the Dirichlet to Neumann map. In practice, it's unjustified to think that all the data that we have lie on the graph of this DM map. So essentially, there are two obstructions. One is that there are only a finite number of measurements available, and also that the data is essentially always corrupted by measurement errors. So here in this talk, we will only focus about the data correction and the infinite precision measurement. So we were not talking about what happened with just a finite number of measurements. So let me talk about the boundary reconstruction. For that, we will, to have an idea and also to try to connect with the most recent work that we have done, we have to recall one of the earliest works about this inverse problem, about the reconstruction on the boundary, that was due to Sylvester and Ullman and consisted in recover the conductivity on the boundary. So for them, what they show is that whenever the domain D and the conductivity gamma are smooth enough, then the DM map can be locally identified with a first order pseudo-differential operator. And its symbol could be expanded in terms of the conductivity on the boundary. The expansion, it was of this type of thing, of this type of extension. So it will be that the first term was the conductivity on the boundary, the second was the normal derivative of the conductivity on the boundary, the third was the second normal derivative at the boundary, and so on. So what happened is that since the DM map was locally described as the differential operator, in order to reconstruct the conductivity and all the higher order derivatives, normal derivatives of the conductivity and the boundary, the only thing we had to understand is to recover the symbols of pseudo-differential operator. And obviously this is something that is well known, how to recover the symbols of a differential operator. Just to point out how it works, think of instead of a pseudo-differential operator, just think of a differential operator, and then try to see that the symbol that we recover is essentially of time using this exponential, this conjugation of the operator P with this exponential. These exponential are usually called in physics, they are just plane waves. These are the tools to recover this information. I mentioned the name because we will use a modification of these plane waves. So then we are going to talk about more recent, but not that recent now, it's 20 years ago already, about how to reconstruct the coefficients on the boundary in a non-regular setting. This started with a work of Brown in 2001, where he used a highly oscillatory Dirichlet data, highly oscillatory solution with Dirichlet data, solutions with highly oscillatory Dirichlet data at a certain point, the point where you want to recover. So the aim of Brown was to recover gamma at the point P on the boundary. And he used these oscillatory solutions to somehow visualize what happened. Think of P as being P0 and this point being on the boundary, and so that the whole domain is in the upper hyperplane of the upper hyperplane. So then what happened is that using oscillatory solution with highly oscillatory boundary data of this type, So looking like this, these are the solutions. So at the boundary, xt equal to 0. So they could look like solutions that are oscillatory in tangential directions. They decay in the normal as the points get into the interior of the domain, and then concentrate at to sort rate m close to the point 0. So these are like essentially are like looking them at the boundary, they look like plane waves that are getting concentrated around the point. So those are the kind of solutions that Brown used and that I mentioned here because they're the solutions that we will use and to filter somehow the noise in the problem with noisy data. So this is what Brown did, and then in 2006, Brown and Salo extended the method to recover not only the conductivity and the boundary, but also the normal derivative of the conductivity at the same point P. Here the tools, as I said, there were these highly oscillatory solutions that concentrate around a point. They were essentially wave packets. Those are the usual way for wave packets are a solution that oscillates and concentrate around a point. They oscillate with the frequency psi and they concentrate around around the point x0. All right, so those are the tools that we will use, and they are also useful. These wave packets will be useful for a later extension that I will mention by the end of the talk. So now I'm going to talk about the Calderon problem with noise. So as I said, the Calderon problem consisted in reconstructing the conductivity gamma from the Dirichlet to Neumann map. As I wrote before, the Dirichlet to Neumann map, it was essentially to know the flux, the current flux on the boundary. So this is essentially is the same as knowing this bilinear form that we have here. So it's the same to know the Dirichlet to Neumann map as just having this bilinear form for every f and every g. So that's just to think of the idea how to model the error, we will start thinking about these quantities that are just complex numbers. So in order to avoid the infinite precision assumption of Calderon's formulation, we will assume that the data we have is just the DM mass, the DM map plus a random error. So the data that we have, it will be this in red. So it will be just the superposition of the signal coming from the DM map plus the error, plus a random error that is here denoted by this E that I draw in purple. So we want to denote this error to denote just a central complex Gaussian whose variance will depend on F and on G. Okay, that's the idea for us. So that will be our data. So just a few comments about the expectation is just since the error we put here are just centered at 0, it means that if you take expectation of the data that we have, we would recover essentially the signal. The idea is that the noise can be filtered having like access to many independent outcomes of the data and just making average of them. The point is that in practice, we will only have a few repetitions of the same noise, and we don't know, we won't know if that's oscillate enough to filter out the noise by making this average. So we don't want to make, for that reason, we want to avoid averaging in the different samples of the same measurement. And what we want to do is just to have, from the same data we have, obtaining the information we want, the gamma, just by a single realization of this data. So we don't want to, let me repeat, we don't want to make average on different realizations. We want to use just one realization and show that that's reconstruct the conductivity gamma. That's what we would like to. And we can do it that at least on the boundary, to some extent. So now the comments is about the variance. It's like the variance, the way that we have formulated, it will depend on F and it will depend on G. And this variable variance aims essentially at modeling the measurement device, which we can think that it decalibrates as the strength of the electric potential on the boundary or the outgoing current on the boundary increases. So somehow this freedom we include is just to, yeah, it can be thing of something like that, just how to model how they calibrates depending of the strength, let's say. All right, so there are different approaches for dealing with the noise. We have to confess that we didn't know much about this, and still we don't know much. So the only thing what we can say is that there are two basic approaches for dealing with the noise. One is a deterministic regularization. This is essentially when the noise is deterministic and small. And the other is using a from a statistical point of view, that you assume that there is no smallness assumption for the noise, but it can model, it is modeled by some type of law, of stochastic law. And recently there has been a work by Abraham and Nickel where they have considered the problem in the interior. And for the condition, the assumption of the error, they were very similar to us, but they have that there is the noise, the variance of the noise has some kind of level, and then the results that they obtain is when the level of this noise it's becoming somehow small. So just to mention that our approach here, it's only about the boundary, but it's stochastic and there is no restriction on the size of the noise. All right, so now let's talk about this boundary reconstruction with noisy data. So I'm going to talk now about, I will present four different results. All of them are related to the Calderon problem. They will consist in two types. They will consist in reconstruction for the conductivity on the boundary and reconstruction on the normal derivative of the conductivity on the boundary. This will be the two types, and now for each reconstruction there will be an exact formula for reconstructing the unknown, and the other will be just a rate of convergence, because in principle we won't be, in practice we won't be able to express the formula because it will come given by limits. So we will talk about how is this rate of convergence of our reconstruction. Okay, so since these the statement of the theorems, the next statements of the theorems are not as nice as this one, I want you to try to understand first this one, because the complexity of the statement will be increasing. So it will be easier if we go like step by step. So here the first result is just reconstruction of the conductivity on the boundary. So there is just reconstruction of the conductivity on the boundary. And the idea is that we prove that with Garcia, we prove that for every P on the boundary, we can find an explicit sequence Fn such that the limit of the data given by this Fn is giving the gamma, the conductivity at the point almost surely. So just two comments here, just two comments here is just to understand that this is a stochastic thing, depending on the realization, and this is non-stochastic, this is deterministic. So what this limit is saying is that essentially this deterministic quantity is somehow, it collapses to some deterministic point, some deterministic value. And this happening in the convergence is almost surely. The other thing we have to say is that these Fn are these wave packets that Brown used in his paper in 2001. So essentially our contribution here has been to show that the noise, it can be filtered using this dirichlet data. Okay, so this is an expression of the limit. In practice, this kind of limits, they won't be useful. So what we want to know is like not to take the whole limit, but to know how close can we get from what we want. So for that is that we write this other theorem that consists essentially in showing the rates of convergence of these limits. So what we show here is just that given a point P on the boundary, there exists a explicit sequence, the same sequence as I said before of Brown, and a constant, so that for every epsilon, we have this quantity. To understand this quantity, let's start thinking first of what we have here inside the red. So we're showing here is just a rate of convergence, right? Because the n is increasing. So we have the difference between something that is random, something that is deterministic, and we are showing that this is getting closer as n increase. All right, so if everything was deterministic, this is just an inequality. But now, since this is probabilistic, what we say is just that the probability that this happen, is as big as we want, is as large as we want. So what it's essentially saying is like a convergence of the rate convergence for being highly probable, this rate of convergence. Okay, so that's about the rate of convergence. Now we talk about how to reconstruct the quantity on the boundary. So now we want to reconstruct the conductivity, the normal derivative of the conductivity on the boundary. For that, we will need to use not only the DM map, but we will also need to use this lambda. Lambda is the Dirichlet to Neumann map of the problem when the conductivity is just 1. Okay, so now the problem is essentially as before. So it's just for every P, there exists a explicit family, this family that we have now, so that we have this quantity Yn. And this quantity Yn, if you see here, it depends on the data that we have. In this other quantity that it's just related to the Dirichlet to Neumann map, with the conductivity equal to 1. So this is something that we know, and for that reason we don't have to put any noise. So this is just the ideal because we know. And there is some average on the parameter of the family. This is the important point here. So we are not just having the formulas used to have in the previous theorems before, but we make an average on the parameter of the family of the solution. This is the key point here. So now what we know is that this Yn is something that we know because essentially is given by the data. And now what we are able to say is that the limit of this Yn as n grows to infinity, we can recover this formula. So we can recover the normal derivative of gamma at the point P, a tangential derivative of gamma at a point P divided by gamma at a point P. And this happened again almost surely. So here, this is a stochastic quantity. This is a deterministic quantity. So there is this collapse to a deterministic value. Here, just to mention that this is the the new P is just the unit normal vector at D, and this tau P is just any tangential vector. So essentially what we recover is about normal derivative, tangential derivative, and gamma. If we recall from the theorems before, we already know that it's in purple because we have been able to recover gamma. So this quantity is known, the gamma and the tangential derivative, and what we are able to recover here is the normal derivative. All right. So now just to mention why this formula has become a bit more complicated, this formula here. So this expression here, now we have to subtract this. To understand this thing, we have to go back to the idea of the paper of Sylvester and Ullmann. So remember that for Sylvester and Ullmann, we say that the lambda of gamma, it was a pseudo-differential operator whose symbol was expanded in this term, in these words, right? So what happened now is that our data like this, it will provide, so we will go to gamma of t when the t is go to infinity. So now if I put the gamma inside this ft, what happens is that it will go to 1, right? So on the other hand, we know that 1, it will be the same as what you would get with the ideal data for gamma equal to 1. So for this lambda, just this lambda. So what we're doing is essentially subtracting so that we kill the first order information given by this. So this is just to kill this information, and we are able to recover essentially the lower order terms somehow in this expansion. And that's why this formula appears. So it was just to mention this. Okay, so now finally we have the rate of convergence in this situation. So now there's not much to say because it's essentially the same. So we have the P on the boundary. There is the family of solutions. Yeah, let me just say that I didn't say in the theorem before. The family of solutions we have here, it was the family of solutions that Brown and Salo used in their paper in 2006. So it's essentially nothing more than that. So the family, it's the same family of the previous theorem. So now what we have is, again, we have defined this yn quantity. And now what we see is, again, the same rate. So, I mean, it's the same kind of expression. It's the rate of this yn, okay? And the rate happened, again, with a high probability. So with a probability as close to 1 as needed. Just mention, because this will be important just to comment now, is that in the first two theorems, there were no average here in the data, while there is no average in the first two theorems, while in the second two theorems, there is an average. We have to average through along the parameter define the family. And this is something that I pointed out because it has brought some further research about this thing. So, all right, so just comments on the result is that the main contribution is essentially just filtering the measurement of the errors almost surely and provide this highly probable rate of convergence, because we are using the wave packets used by Brown and by Brown and Salo. And then just to mention that the first two theorems, there were no average. And the reason was that the wave packets used there were so good that the L2 norm of the weights packet were decreasing. So they were vanishing. So that what happened is that essentially, this is roughly the idea, is like, since these quantities are getting smaller, what happened is that the variance of the noise is getting smaller. So that means that essentially the sequence you have, it's going to 0 at least like for almost every realization. So that's essentially the idea. For the second theorem, what happened is that that we need an average. We need an average with respect to the parameter square root of n. And the reason is that these quantities, the weights packets that we need to use to reconstruct the normal derivative on the boundary, they are not anymore vanishing. So they are just bounded. So one has to do something else. And that's why the average come in. So that's the role of the average. So then a natural question after this result that I have presented is like, can we recover further? So can we recover the other terms of the expansion that Sylvester and Ullmann recover for every G and for every G? So I pointed out here that we have just recovered for G equal to 0 and G equal to 1. So what happened for G greater or equal than 2? Can we do something? So I will keep this question until the end. All right, so what is the underlying idea here? So the underlying idea is just the strong law of large numbers. So recall that the Short law of numbers tell you something about how the average, the average of independent sequences, independent random variables, converges to the somehow to the average of the means, of their means. This essentially happens by using two ingredients. One is that the random variable are independent, and also that the variance are not growing so much. So the variances can grow, but not that much. So then this is essentially what it's going on here. So in our expression, this would be the random quantities, or yes, this is the random, because this is deterministic. And what we have to see is just, since there is the variance in our sequences don't grow so much, the only thing we need to control is somehow that there is enough uncorrelation. And that's essentially the analysis underneath. There is some oscillatory integrals and so on, but I mean, the underlying idea is just the uncorrelation of this data. Okay, now I will spend a few, as I mentioned at the beginning, I will explain more about the modeling the error, and the reason for that essentially because we didn't know that, and maybe, I mean, obviously in other communities it is like very well known. It wasn't for me, so I mean, I will show it. I will show it. This is totally standard. I mean, I have to say that this is totally standard, and we're just learning as students. So this is I will talk about what is the definition we use about white noise. So the white noise here is to define, we consider a probability space with this omega fp, and then we consider a Hilbert space. So we say that the linear map W going from the Hilbert space to the L2 of this probability space is said to be a complex Gaussian white noise if two things happen. One is that for every F in the Hilbert space, the image, this WF, is a center complex Gaussian variable. This is one of the things. And the other is just this linear map is just an isometry. An isometry of this way. It's an isometry so that the expectation of the multiplication of these two random variables is equal to the inner product of F and G in H. So this is the definition we use for the white noise. Just to mention that this denotes the Hilbert space the inner product in the Hilbert space H. So this is about the definition, and now to show that this white noise exists is rather simple, at least in separable Hilbert space. So the only thing that in separable Hilbert space, or whatever the probability space, is so that there exists a sequence of independent complex Gaussian variable. So in complex variable that happen that they are centered at zero, so expectation zero, and so that this quantity that is essentially the variance is equal to 1. So in this situation, there is always exists this complex Gaussian white noise. And the way to define is essentially is just through defining, or through considering an orthonormal basis on the Hilbert space and defining this WF as, we could say, as the Fourier coefficient. So this WF would be just the sum of the inner products between F and En, so this is the Fourier coefficient, multiply, instead of by the element of the basis in the Hilbert space, by this Xn, which is the random variable. And in order to make sense of this, we take the convergence in the sense of this of L2. Okay, so now this was an abstract definition depending on the Hilbert space H that we choose. So now the model of the error that we have for the Calderon problem is just that we define this error E, and they have to be from the complex Gaussian white noise. So we will define this epsilon through this W. And for that, we take the Hilbert space that we take is just the tensor product of L2 on the boundary. And the error, this error that it depending on F and G, it would be just defined by W, by the white noise, tested in this F and this G. So recall that how was the inner product? The inner product in this Hilbert space is essentially the product of the inner products of each of these. Okay, so now in this situation, after these definitions, one can see actually that the data that we have, it was the Dirichlet to Neumann map plus some error that it was given by this product. This is a sum of two indices. These are the coefficient, the Fourier coefficient of F. These are the Fourier coefficient of G, and these are just random variables that depends on the indices alpha 1 and alpha 2. Oh, sorry. And this random variable were just the white noise tested on these elements of the basis, where this AN, they were nothing more than form an orthonormal basis of this L2 on the boundary. So yeah, just to say that with this definition of the data, again, this is a complex Gaussian. The expectation of this data is just the ideal data. And that the variance that we have here, it will depend on the norms of L2 of F and the norm of L2 of G. So that's why when the wave packets has L2 norms going to 0, the averaging were going to 0. Sorry, the error was going to 0 and no average was needed. Okay, so now let me talk about a couple of extensions about this method. So the first station was in collaboration with Lei, Ling, and Zhou, and we extended the results for Maxwell equations. Recall here that Maxwell equation is a system of two vector equations where E denotes the electric field and H denotes the magnetic field. And we have the parameters, the parameters we consider here are the electromagnetic parameters coming from the this was the magnetic permeability, and this is like, let's say, a complex conductivity that contains information about the actual conductivity, but also about the electric permittivity of the medium. So in this situation, one can set up like a problem that is very similar to the Calderon problem, with an analog for the Dirichlet to Neumann map, which in this case, it would be just a mapping that take the tangent component of the electric field into the tangent component of the magnetic field. And with this Dirichlet, let's say Dirichlet to Neumann map, but with this boundary data, one can reconstruct mu and gamma. U and gamma, this is like the first statement is that we can recover that with ideal data, but also if we add some error as we did before, so this data plus some random error, we can still recover the conductivity, these coefficients, the magnetic permeability and this complex conductivity almost surely. But in this situation, it was interesting to point out the different two things. Here, what happened is that we did this somehow like like separately, and then we gathered what we had. And from one side, one of us tried to define the model in L2 spaces, while others tried to model in H-1. The reason why some of us tried to model this in H-1 is because the wave packets that you have to use to construct these coefficients in the deterministic situation were so that they have no decay in the L2 norm. So there were no decay. So modeling this thing in L2 had problems. So some of us decided to do it in H-1, And on the other side, some of us try to do it in L2. And what happened is that whenever we use the L2 as a base, as a model, we need to use the averaging. So in order to reconstruct the mu and the gamma, we need to use to perform this averaging on the family of the parameters, as I show you when reconstructing the normal component of the normal derivative of the conductivity. So this second set of theorems that I have shown that require the average. While when we were trying to do this in the model in H-1, there were no need for this averaging. And roughly speaking, one of the reasons is that when modeling the noise in L2, what happens is that any kind of oscillation that you put on the data are totally killed. They are just killed. So no matter what is the oscillation that you put on the inputs, whenever you are in the L2 norm with the L2 error, this oscillation is killed. So there is no change on the error. The error doesn't change with the oscillation. However, in H-1, what is happening is that the oscillation of the weight packets we are testing for the noise, what it's doing are just like playing a role in favor of us. So this H-1, what it's doing is counting the oscillation in a favorable way. And that's why we don't need this averaging. That is something we see now and we understand now, and we understood this after generalizing this problem to other situations. So that's why we came to this other problem that I will show you after, that is a problem about observability with noise. We say, if I'm honest to you, I would say that this is essentially an academic problem to understand what was going on in this other situation. But it is true that it could be thought also as something with application in quantum mechanics because of the setting. So the truth is that we were only thinking of this problem as an academic problem, but we are using the language of quantum mechanics to express some of the things that are happening here. So just to say, to understand the role of the choice of the Hilbert space in the error, so we will introduce a different problem. So we will introduce a problem that consists of recovering an observable P from measurements MP that contain some random errors. Okay, so the observable P's here are pseudo-differential operators. So these pseudo-differential operators are described essentially with this expression that is the natural one for pseudo-differential operators. Whenever the symbol A is a very particular type, is of a classical symbol and of order M. Okay, and the measurement that we have are this quantity MP of Fg, as we somehow did for the Calderon problem. This is the signal now, the signal we want to recover, the signal, the ideal data, and this is superposed with some random error with the noise that we have here. Another thing is that we have introduced a parameter beta on the noise just to measure, to somehow quantify or state at every time, at every moment, in which level are we considering the Hilbert space. So in this situation, we are considering the Hilbert space as the tensor product of two Sobolev spaces, but now the Sobolev space will depend on the parameter beta. So now what happens is that different betas correspond to different variances on the error that we have here. So now I repeat the comment that I made before. It's like now what happens is that if beta is equal to 0, these are just L2 spaces. So the oscillation of F and G, so the oscillation of these functions that I'm using, do not affect the size of the error, only their masses. Only the masses of the F and the G are important for this kind of error. However, if my beta is positive, the noise will increase with the oscillation of F and G. While if beta is negative, the oscillation reduces the size of the noise. So that was going on here before. So no needed of averaging, this was because the oscillation was somehow reducing the size of the noise. So it was easier to to eventually filter the noise and find the signal. Okay, so now in this situation, the problem we had was just to the problem we had, it was the observational limit of wave packets. So now it's like we want to use wave packets as we did it with the Calderon problem to really see what we can extend, what we can understand about the expansion of these classical symbols. Okay, so this is what we want to understand, and we use the wave packets, and we want to know up to what extent we can see this symbol. So now what happens is that we have this expansion, and what we are saying here is that this expansion, this expansion is so that this AJ are also classical symbol of order MJ, and there is a decreasing, the order of the symbols are decreasing. And we also assume that they are homogeneous in the variable C, This formulation recalled quite a lot to what happened to the problem that Sylvester and Ullmann solved in the deterministic case. So now what we did in collaboration with Meronio was to show that with the wave packets, we were able to reconstruct a first set of symbols. So we were able to reconstruct part of the expansion of this symbol. So we were able to recover some of them. And these symbols we recover almost surely using these wave packets. Okay, but what happened is that why I put the color of sorry. So yeah, so I put different colors for the first and the last. It's just because for some of them we don't need average. For the first G-Bay we don't need average, and for the second part we need the average. And as is obvious, the order, there is a relation between the order of the terms in the expansion with the level that we put on the Hilbert space, on the Sobolev space, and also at to what kind of order we can recover. So this is this relation between the orders and the beta. And now what happened is, as I said before, is that the first two can be recovered with using no average. And for the other tools, we need average. And furthermore, we were able to prove that it's not possible to use wave packets to reconstruct the final part of the expansion. So the more regular part or the more regularizing part of the expansion is actually lost. We cannot recover using wave, at least with wave packets. So what the message is that the signal is lost in the noise. So just a particular case to keep in mind in this abstract setting, or just like some conclusions that we can keep in mind that could be useful, is that if P, the observable, is just a differential operator for the M, we can recover the full operator P from the data that we have that depend on beta on the level, whenever the beta is smaller than 1/4. So that means that even when the error gets amplified with the oscillations of the wave packets, we're able to recover the full symbol of the differential operator. So for example, if the differential operator were elliptic, we were even able to reconstruct like parametrices and so on and so forth. And now, after these comments, if one thing, and remember the question that I make is like, how can we like solve or reconstruct the full expansion in the Calderon problem? So the answer to this question is that using wave packets, it is not possible to recover the higher order derivatives of the conductivity for J greater or equal than 2. Unless we change the level of the noise, meaning we change the space, the Hilbert space through which we change we measure the noise, we only can recover what we did with Andoni Garcia. Okay, so just the conclusion, just to end up. So let me just mention that the Calderon problem is a theoretical model that arises in electrical prospecting, that implementing the model presents non-trivial challenges. It assumes, because the formulation assumes infinite precision measurement and infinite many pieces of data. We are here, we have only considered the data corruption, and we have followed a stochastic approach that provides reconstruction on the boundary, but they are almost surely. We also show that or provide some high probable rate of convergence. So that's essentially to show like what is the rate of the convergence. Then just to mention that the key underlying idea is just the strong law of large numbers. So one has to use one has to prove like some kind of correlation with the weights package we use. We say that these results can be extended to Maxwell equations. And yeah, and then there is a freedom in the choice of modeling the error, and different choices respond to oscillation in very different ways. So this can be used to model how the inputs respond to these oscillations. And finally, we have shown that white packets are useful but have limitations in the problems of observability with noise, because we have shown in the situation of the observable, we cannot recover the full expansion. We can only recover part of it, depending on the order of the operator and the level that we put on the Hilbert space defining the white noise. Okay, and I think that's all I wanted to tell you. So thank you for your attention.
Thank you very much, Pedro, for the very nice talk. Thank you very much. Are there any questions or comments? Yavar, you're very welcome.
Hi, Katya. Hi, Pedro. How are you?
Hi, Yavar. Fine. Good to hear you.
Yes, thank you. So I was wondering if you couldn't try something with recovery of nonlinear term with the material that you're considering here, because thanks to what has been proved by Isakov, there's a strong connection between recovery of coefficient at the boundary and the recovery of nonlinear term. So I was wondering if at some point you couldn't tackle these kind of things with your material.
So I have to confess that I haven't thought about that, but it could be nice actually to look at it, like to see if you could recover the nonlinear term. But my answer is that I don't know at this point.
I think you can do something, but
Right,
maybe you should look at the work of Isakov about these kind of things.
All right, thank you. So that could be great to look at it.
Yes, thank you.
Thank you.
Thank you very much. Are there any other questions or comments, please?
Okay, so I have a question.
Please.
Okay, so question is about one of the last points that you made, how you model the noise in the first place.
Yes.
So let's say you're looking at the quadratic form. Let's say that you're looking at the linear operator only. That doesn't seem to be equivalent to just adding white noise, right?
So you mean in this formula here?
Right, but it's a quadratic form. Let's just take n applied to f, which is the linear operator.
Yeah. So it's true. In terms of operator, if you look at in terms of operator, I'm not adding white noise. So what I would do somehow doing is adding some kind of operator that at every f I give you a white noise.
Okay, so so the other question is why choose this noise model? Somehow you're adding noise to the quadratic form in a way instead of the linear operator.
So yeah, so the reason at the beginning is we didn't know how to define, and what we thought is that these quantities here are somehow like they are complex number in the model that we have, but I guess in practice they would be just real number, and I guess these numbers are the things that you get as an output when putting the data. So we thought that this number would be the ideal data, and they have to be somehow like distorted with some kind of Gaussians. So whenever you are given an f and j, these are just like a regular Gaussian. So that was the reason why we thought about setting the model this way. So from the beginning, we thought like at every moment of this, we had a Gaussian variable that depend on f and g. And that was the reason why we modeled the error in this way.
Yeah, it looks like some kind of multiplicative noise actually, because it scales with f and g, right?
But I'm not multiplying the random. So the random variables, I'm not multiplying. Random variables are just this. So there is no multiplication between the Gaussian, the Gaussian. So there is just one Gaussian. So I would say it's just like a linear thing, but the Hilbert space that is used is somehow bilinear.
Yeah, but if you multiply f by 10, you're going to multiply the noise by 10. So this is what I mean, that it scales with f.
All right. Yeah. So in that sense, I guess so. Yeah. But you know, on the other hand, this is the way that I see is like checking that the random the variable that you have here, it's like increasing the variance of the noise is increasing not only with the voltage but also with the current through the boundary.
Okay, so it's different from additive noise. Okay. Well, okay, thank you.
Okay, thank you for the questions.
Thank you very much. Are there any further questions or comments? Are there any questions or comments? Okay, if not, thank you very much, Pedro, for the very nice talk. Thank you very much.
Thank you.
Thank you very much, everyone, for joining the seminar. Thank you.
All right, thank you very much.